Okay, so for this lecture, we are going to be covering the chemistry unit or chemistry chapter. So I'm going to ask you to find your chem packet, and at the top it should say Biochem Introduction. So that is the one that you will want to work with and take notes on as we move through this information. When we look at biology, and even when we get more specific and we start talking about anatomy and physiology, chemistry is going to play a very important role in that because even though in some respects it's a very different branch of science, there is a lot of overlap in anatomy and how things function in the body. So we do need to have a basic understanding of chemistry and some of the properties of chemistry to fully be able to understand more the physiology side of things when we're talking about anatomy phys. So we do take some time to cover chemistry information. Now, I have people that have not taken chem classes in some cases. I have people that are not overly fond of chemistry, and I have people that have taken chemistry, but it's been a while. So don't worry, we just need to know our chemistry information at a foundation level. So I'm going to go through some things that are pretty basic in the world of chemistry. And if you've had chemistry in the past, hopefully it will come back to you fairly quickly. So the first question that I have there, why do we need to study chemistry and anatomy and phys class? And as I mentioned, how atoms work, how particles work when we start talking about positive and negatives and that interaction, that is really the driving force behind a lot of the things that take place within the human body. So when you understand that, then you can start to link that to how a cell works, what it's able to do, and beyond that. So that is why we take a little bit of time just to go back and brush up our chemistry information. It also talks about your body functions are going to depend on cellular functions. And one of the things that I find when we start talking about the body, especially when we start talking about cells, is that people have this image in their minds that cells are building blocks. So if you were going to build a brick wall, you would take individual bricks, you would link them together and create your wall. But while that's one part of what cells do, it's not the only thing that they do. You also have to think of your cells as being tiny little factories because they are constantly producing products. So, yes, they build material, they build tissue. They're also going to create cellular products that will be used all over the body. They will be used to build your DNA. They will be used for your muscles. They will be used for your hair. All of the things that you have in your body have to be built from the ground up. Because if you think about it, the food that we put into our body to give us energy, there is nothing in our bodies that is made out of those foods. Your cells have to break it down. They have to get it into its simplest form and then recombine it in a way to produce your bone cells, to produce your muscle cells, and all those different things. So your cells are actually tiny little factories that are working to make all the products you need to build the parts of your body. So yes, they are building blocks. They're also factories. And as I mentioned, your chemistry information is going to lean more towards the physiology side of things, the functionings of how your organs work, and getting a little bit better understanding of that process. So if you want to take a look at slide two talks about the structure of matter. And these are just some basic terms that you typically hear in chemistry class. So we talk about matter, we talk about elements, we talk about atoms. With matter, the definition is pretty basic. If it is going to have mass and if it's going to take up space, then we classify it as being matter. When we look at elements, elements are going to be made up of the exact same atom. So it mentions in the definition that they are identical atoms. When you cluster a bunch of identical atoms together, we refer to that as an element. And if you've ever seen the periodic table, you've seen an example of all the different elements that are out there. So when we look at those elements, because you are building material, like I said, your cells are constantly building product so that you can make all the different things in your body. It's going to come from having those different elements available to it. So it talks about bulk elements and trace elements. Bulk elements are going to be those elements from the periodic chart that you need to have in your body, but you need to have them in large amounts. So your body is using a lot of it, and so we need to make sure that we get a lot in. Trace elements, your body needs to have it to function well, but it doesn't need to have it in huge amounts. So this actually ties into having a good, healthy, well-balanced diet, because in order to get the bulk elements covered and the trace elements covered and make sure that you are getting them in your system, you have to eat a wide variety of foods to make sure that they are getting replenished in your system. Because if your cells are tiny little factories and they're constantly producing product, they're using those elements up. And so eating in a way is replacing those elements to make sure that you always have them in stock. The body has an amazing capacity to find a way to do what it needs to do. And so if you are not giving it the elements it needs through the foods, excuse me, through the foods that you're eating, it is going to then start pulling it out of existing tissue and things that it's already created. So well-balanced diet is very important for a wide variety of reasons. The last one that you have on there talks about atoms. Atoms are going to be the smallest individual units that you have within an element. Now, an element is made up of all the same atom, but if you're looking at just one of those parts of an element, then you would refer to that as an element. So they're an atom. They are the building blocks of the element. If you move on to slide three gets into the atomic structure. So if you were able to actually see an atom, this is the gist of what it would look like. You would have a central core to the atom, and then you would have an orbital around that core that would be referred to as either the shell, the electron cloud, the orbitals. Some people refer to them as the rings. They get a wide variety of names, but we're just referencing that space that is going to be located around the nucleus. Now, the design of an atom is very specific. You have that central core of a nucleus, and what you are going to find there is 2 out of the 3 particles that make up an atom. So your protons and your neutrons would be located in that nucleus. Now, the protons give off a positive charge. Neutrons have no charge. So they cluster together and they make this nucleus. And because the protons are giving off a positive charge, neutrons are not giving off any charge, the overall pull of that nucleus is going to be positive. If you think about what you know about laws of attraction, the laws of attraction are going to, or they state that opposites attract. So if I've got this positive core, it's going to draw negative charges to it. And that's where the electrons come in. So if I've got 1 positive charge in my nucleus, it's going to draw 1 negative charge to it. Or if I've got 5 positive charges in my nucleus, it's going to draw 5 negative charges to it. And that's how we get that outer area where the rings or the electron clouds are located. That is where the electrons are going to live. Now, in the human brain, we like to have concrete things for the most part. Abstract is a little bit more difficult to kind of visualize. So when we draw our atoms, we draw circles around the nucleus and we dot in where the electrons would be located. In actuality, the electrons do not have a fixed spot. And what I mean by that is that positive nucleus draws the electrons in, but the electrons don't stay in one location. They will orbit and circle around the nucleus. They pretty much stay the same distance away, but they have the ability to move and float around that nucleus. Now, with the electron clouds or the orbitals, different science teachers will refer to them different ways depending on the teacher that you had. You'll notice here that we have 2 rings. And for our purposes, we only really need to know the first 2 rings. So electrons are placed in the orbitals, but the orbitals can fill up. So if you go to a movie theater and you go to watch a movie and you're looking for a seat, if you find a row that is completely filled with people, you're not going to sit down in that row. You're going to go to the next row that has openings or space for you. So think of those electron clouds or those orbitals being the same way. They have a max capacity. And once they reach that, no more electrons can go into that ring. They have to go to the next one. So the first orbital that we have can hold a max of 2 electrons. Once there's 2 electrons in there, now you have to go to the next orbital. And so the next group of electrons would start to fill in that next orbital. The second one can hold a max of 8. And there's more to it than that, the more rings that you add. But for us, we just need to know the first 2 orbitals. So the very first orbital around the nucleus can hold a max of 2. The second orbital can hold a max of 8 electrons. If you move on to slide 4 talks about some of the common terms that you hear in chemistry. So we've got molecules and compounds. When you look at the definition for the molecule, it talks about a particle that you would get when 2 or more atoms chemically combine. Now, the important thing to keep in mind here is that 2 or more atoms, so you could have multiple hydrogen atoms coming together that would fall into that category or under that definition. Or you could have multiple oxygen atoms coming together. Compound is going to be a little bit different because this is when you get a particle or a substance that is formed when you have 2 or more atoms of different elements. So there is a distinction between those two. Molecule is when you have 2 or more atoms chemically combined, but a compound is going to be when those atoms are from different elements. And then the last one just references the molecular formulas and what that would look like. So a molecular formula is just writing the element, the symbol for the element, and then indicating how many you have of each one. So for the first one, H2, that is going to indicate that we have 2 hydrogen ions. The next one, C6H12O6, that is your basic sugar. So that's telling us that we have 6 carbon, we have 12 hydrogen, and we have 6 oxygen. And the last one, H2O, indicates that we have 2 hydrogen. And if there is no number behind it, like we see with the oxygen there, that is an understood 1. So we have 1 oxygen molecule. But if we talk about molecular formulas, that's what we're talking about, giving the symbol for the element and then also indicating how many you have of each one of those. If you look at the next slide, and I do this a lot, I will put in like an explanation of it, and then I'll put a visual representation too. So kind of cover different learning styles. This is the same information that was in the previous slide. It's just doing it with pictures to show you the difference between what a molecule would look like and what a compound would look like. The next one goes into isotopes. And in a perfect world, if you have 3 protons, so 3 positive charges, then your element would also have 3 neutrons to match that and 3 electrons. So those 3 particles, the positive protons, the no charge neutrons, and the negative electrons, you would all have them in the same number. That's in a perfect world. But we always have an exception to the rule, and isotopes is one of those exceptions. So an isotope is a situation where the number of protons and neutrons in the nucleus don't match. So perfect world, if you've got 3 protons, you've got 3 neutrons. But in the case of an isotope, you would have 3 protons, but maybe you'd only have 2 neutrons. Or you'd have 3 protons and you would have 4 neutrons. Whenever the number of neutrons and protons do not match in that nucleus, it is referred to as an isotope. Now, why do we care if those two don't match? The reason for that is when you put the protons and the neutrons in the nucleus together, they cluster and they bond together. When they are not in even amounts, that cluster will break apart every so often, and it will eventually come back together, but then it breaks apart again. And it repeats that process. We don't see that when all the particles are balanced with each other and in the same numbers. But as soon as you get different number of protons and neutrons, that nucleus will break apart and then come back together. Now, what does that lead into? Every time that the protons and the neutrons break apart, there's a release of energy. And you guys know that as radiation or being radioactive. So when you talk about something having radiation, what that is telling you is that it's an isotope, and the nucleus within those atoms every so often is breaking apart and then coming back together. Now, the cool thing about that is you can actually predict based on the element that you are dealing with, it will have what's called a half-life, meaning that every so often at the same rate, that nucleus breaks apart and then comes back together. So it might be every 500 years. So the nucleus is together, 500 years, nothing happens, then all of a sudden it breaks apart and it comes back together. And then 500 years later, it happens again. Others, their half-lives are a matter of seconds. Every 2 seconds, it breaks apart and comes back together. Now, the thing that you can do with those elements that have longer half-lives, carbon has an extremely long half-life, over 5,000 years. So what they can do with that is they can actually do what's called carbon dating. So we can look and you can tell how many times that nucleus has broken apart. And we know that because that happens every 5,000 plus years, that every time that's happened, 5,000, 10,000, 15,000, you can then say how old that particular item is. So when you have scientists saying, well, this is 30,000 years old, what they're referencing is how many times that half-life has taken place. So a lot of cool things that you can do with isotopes, but obviously the fact that they give off radiation, depending on how much radiation they're giving off, they can be problematic as well. The next slide that we have talks about bonding of atoms. And with the bonding of atoms, I jumped the gun a little bit. I already talked about the number of electrons that you can have in the first and second shell. We don't need to worry about the third shell too much. But bonds happen because of how atoms behave. Atoms want their outermost shell to be completely filled. That is when they are happy. So your atom has that first shell, and if it only has one electron in that first shell, well, if you look there, that first shell can hold up to 2. So that atom would not be happy because that shell is not filled up with electrons. So when bonding happens between different atoms, what's actually going on is those atoms are working to get their shells, outer shells, completely full. And so they will give up electrons, they will gain electrons, whatever they need to do in order to get that outermost shell completely filled. Let's say that an atom has 2 orbitals. We know that that second orbital can hold up to 8 electrons. So let's say that second orbital has 7 electrons. What's going to happen is that atom is now going to go around and it's going to look for one more electron to pick up. And it will find that electron, it will put it in that outermost shell. Now that shell is at 8, it is completely full, and that atom is happy. So that's why you can take some elements and put them in the presence of each other and nothing happens, because their outermost shell is full. It's not looking to give up or to gain electrons, so you're not going to see anything happen. In the other case, you can put 2 elements together and you get bubbling and smoking and all these things that happen because they are moving and shifting those electrons to get their outermost shell full. So atoms, in order to be happy, want that outermost shell to be completely filled. Doesn't matter if it's the first shell, second shell, third shell, whichever one is their outermost shell, they're going to work to make sure it's happy. Now, how they decide if they gain electrons or if they give up electrons depends on how full it is. So let's say we have an atom that has a second shell, but there's only 1 electron in that shell. Okay, going back to the information you have here, it has 1 electron right now in the second shell, but it can hold a max of 8. So that atom has to make a decision. Is it easier to give up that 1 electron Or would it be easier to go out and find 7 electrons? Well, obviously it's going to be much easier to kick out that 1 electron. Then it drops back to just having 1 shell. That shell already has its 2 electrons, it's full, and it's happy. The other example that I just gave you, if we're working on that second shell and it has 7 electrons, it's only 1 away from being full. So it would be a lot easier to find an electron and bump it up to 8 and be full than it would be to try and kick out 7 electrons. So how atoms behave and react with each other depends on that outermost shell and trying to get it full. And then depending on the number of electrons that are there, what is the easiest route? Is it easier to kick out electrons, or is it easier to pick up electrons to get that shell completely full? So the next slide that you have shows the bonding of atoms, and it gives you the 3 different examples. The first one that you have, hydrogen, that is sitting there with 1 electron. What it's going to do is it's going to look for 1 more electron to fill that outer shell. Helium that you're looking at, helium is happy. Helium is number 2 on the periodic table. It has 2 electrons in its outermost shell, and so it doesn't need to do anything. It's stable because that outer shell is filled. Then we have lithium. Lithium is number 3. So we put the first 2 electrons in that first shell. It can hold a max of 2, so that first shell is full. But lithium has 3 electrons, so now we have to go to the next shell or the next orbital to place that final electron. Well, once we get to that second shell, we know that that shell can hold up to 8. Lithium is going to donate that 1 electron. It's going to kick it out and get rid of it because that's the path of least resistance, or the easiest way to go. If you look at the next slide, it talks about ionic bonds. Ionic bonds are get their name from ion. Ion is a term that means it carries a charge. So ION, little word, means that it's going to carry some type of charge. So if you're just being very general, you would refer to it as an ion. If you want to be more specific, you could use cation and anion in order to reference what's going on. So when we talk about cations are positively charged atoms. Anions are negatively charged ions or atoms. If those are terms that you're not overly familiar with, easy way to remember it is anion. AN stands for a negative ion. So 3 terms that you just introduced there. The term ion, a general term to indicate that an atom carries some type of charge. Doesn't tell you if it's positive or negative, but it just means that it has a charge. If you want to be specific, you would use cation to indicate that the atom has a positive charge, or you would use the term anion to indicate that the atom has a negative charge. So in the case of ionic bonds, what happens is this is where electrons are going to be kicked out by 1 and then gained by a different atom. So 1 will donate an electron essentially, and it will get to a point where its outermost shell is full. And then another element out there that needs electrons will then pick up those electrons that were donated by the other element. So it shows you sodium and chlorine, and that is the example that it uses. In the case of sodium, if you look at the electron configuration that it shows you, it has a total of 11 protons. And so what happens is you put the 2 electrons in that first shell, 8 electrons in the next shell, and then you still have 1 more to place. So we haven't talked a whole lot about third shell, but you would have to go onto the third shell to place that 1 electron. Well, that 1 electron does not fill that third orbital by any means, so sodium kicks it out, gets rid of it. And then what will happen is chlorine needs an electron to fill or complete its outer shell. So when sodium kicks it out, chlorine will pick it up, add it to itself, and you'll notice that there's a little positive next to the sodium and there's a little negative sign next to the chlorine. A few minutes ago, I mentioned that atoms like to be balanced. In a perfect world, you would have the same number of protons, same number of neutrons, same number of electrons. So that if I have 10 protons and 10 electrons, they cancel each other out. But when these electrons start shifting, an element is going to now have more electrons than protons or fewer electrons. So as soon as that sodium kicks out the electron, it now has one more proton than it has electrons. It has more positive charges than it has negative charges because it gave one electron the boot. So it is now positively charged. We would call that a cation. The sodium picked up that electron, so it was balanced. It had the same number of protons, same number of electrons, but now all of a sudden it grabbed that extra electron so it could get its outermost shell full. So now it's carrying more electrons than protons. It has more negative charges than positive charges. So we give that a negative charge, call that an anion. So this kind of sums up what we were talking about. Again, a little bit more of a visual, if that is your style of learning, to back up what was just explained in the previous slide. The next one that we have talks about covalent bonds. Covalent simply indicates that you are going to have two atoms that are going to share their electrons. So nobody is giving any up and kicking them out, but instead two different atoms are going to combine and latch to each other, and they are both going to use the same electrons. So you see here you have the hydrogen atoms. They each have their one electron. They need two in order to fill their outer shell. So they will simply come together and they will share the two electrons between them. Outer shell is full, they're happy, and that is an example of a covalent bond. The next one that we have talks about polar molecules, and polar molecules are really interesting in the world of chemistry because they actually create atoms that behave like a magnet. You guys have all worked with refrigerator magnets at some point in your life. You know that one side is positive, one side is negative, and you've kind of pushed magnets around each other and seen the reaction that you get. Now, when you look at this example, this is water that you are looking at. H2O, two hydrogens, one oxygen. The oxygen is the larger molecule, the hydrogen are the two smaller ones. Now, typically when you have things combined together, those two hydrogens would not be on the same side. They would want to be equidistant from each other. That is how most things are going to behave in chemistry. But you have these, again, exceptions to the rule, and this molecule is one of them, where those hydrogens go to the same side and they are not spread out from each other. So what happens is those hydrogens are going to get bullied by the oxygen. The oxygen actually pulls the electrons away from the hydrogens and holds the electrons to itself. So the oxygen side of water actually behaves negatively because it's stolen those electrons from hydrogen. Well, as soon as those hydrogens no longer have those electrons, all they have left are their protons, their positive charges. So that side of water is going to behave positively. So a polar molecule is simply a situation where you have an atom that behaves like a magnet. One side is going to have a positive charge, the other side is going to have a negative charge. We're going to skip over the hydrogen bonds for right now and jump to chemical reactions. So again, just a couple terms that you typically would hear with chemical reactions. The first one, the definition for chemical reaction itself, simply states that you have chemical bonds form or break between atoms, ions, or different molecules. So chemical reactions, simply taking what you initially had and then recombining it, reforming it in a different way. Reactants would be what you have going into the reaction, and then the products are what you have after the reaction. So if you think of an addition problem, 2 plus 2, those are your reactants. 4, that is your product. So a little bit different way of kind of referencing it or talking about it. And then it gives you the example at the bottom of the page there. The next slide that you guys have talks about acids, bases, and salts. We hear a lot about acids and bases, but a lot of people, again, have kind of a misconception or a different view in how they look at acids and bases. The first term that we have there, electrolytes, are simply going to be substances that release ions in water. And it gives you the example of NaCl, so the sodium and the chlorine. If you guys know the molecular formula for salt, that is what it is. So we talk about electrolytes, and if you've ever looked at a sports drink, they will talk about the fact that they have electrolytes. It's a fancy way to tell you it has salt. And sodium chlorine is not the only salt that there is. It's the most well-known one that we use and come in contact with. But essentially, when you have electrolytes in a drink, you're taking in salt. And if you've ever held a sports drink in your mouth long enough, you'll pick up that salty sensation. It just sounds better if they say electrolytes. Then when you look at acids, acids are going to be substances that release hydrogen, and bases are going to be substances that can combine with those hydrogen. Now I'm going to take you through some material on the periodic table when we come back face to face. So I am going through this a little bit on the faster side, just because I know this is a conversation we're going to have when we come back face to face. The next slide that you have shows you what the periodic table looks like. So the periodic table ranges from 0 to 14. 7 is the midpoint, that is neutral. That point, you do not have any acidic properties, you do not have any basic properties. As you start going from 7 down to 0, you become more acidic. As you go from 7 up to 14, you would become more basic. Now you'll notice the diagonal split in this. That is actually a slide that's showing you the number of hydrogen ions you have compared to the number of hydroxide ions that you have. So as the number of hydrogen ions increases, the number of hydroxide decreases, and vice versa. So the more hydrogen ions you have, the more acidic it is. The more hydroxides you have, the more basic it is. And again, I'm going to go through this with you guys, so please make sure that this packet comes back with you to our next face-to-face meeting. And then the last slide that you have there just gives you some basics in reference to the body. We want our pH to be at 7.4. That is our prime set point for pH. As long as you're between 7.35, 7.45, things are working where they should be. Once you start getting away from that, it's not a huge parameter that you have to work with here. But when you get from 7.5 to 7.8, that would be referred to as alkalosis. So your pH is getting more basic, so alkalosis. And then if your pH goes from 7.3 down to 7.0 and starts moving that way, on the periodic table, we're actually getting closer to 0, which would shift us more towards the acidic side. And so that's why it's referred to as acidosis. So as I mentioned, this packet needs to come back with you guys the next time that we meet. Please also check in Blackboard for your assignment that will also need to be done the next time that we come back to class.